Alrighty then, hello and welcome. Thanks for joining us. It's great to see you. So let's take you back in time when dragons ruled the land, and we've got a problem. Um, the Iron Bank is going bust. Someone has been conning them out of all their cash. So they've asked us to come in and help and investigate and find out what the problem is. So it's time we're going to apply some modern techniques to the age-old problem that is of fraud. So we need to investigate who's been up to dodgy dealings, and we'll do that with a combination of SQL and machine learning. So, hi everyone, I'm Chris Saxon. I'm part of Stephen Feuerstein's Oracle Developer Advocate team. It's my job to help you get the best out of Oracle database and hopefully have a little bit of fun whilst doing so. So I'll be covering the SQL side of this. To cover the machine learning, I have Abby with me.
Hi everyone, Abby Giles Haig. I'm the Chief Data Science Officer at Vertice, and I'm going to help Chris understand the world of machine learning and hopefully have a little bit of fun with machine learning alongside your SQL, Chris.
Okay, cool. Sounds good. Alrighty then. So what's happened is, so the Iron Bank, they've got their massive tome, the big book with all their transactions history in it, and they've given that over to the hand of the king and said, look, just go through this, find the fraudulent transactions, and see if you can find some common rules that have caused this. So then when things happen in the future, we can flag them up and, try and catch people a little bit sooner than we are doing currently. So they went through and poured through these pages and pages of details, and it took them several days. It probably took them several weeks, in fact. And they went and they found two common things which they identified as common causes of fraud. So the first of those was pretty straightforward. There was a lot of transactions, fraudulent transactions, with a value of exactly 10 million, which is just a bit weird, right? It's common to have like high value transactions, but when they're all an exact round number, it's a bit suspicious. Usually like 9999, 9,999,000 or something like that. So we got a lot of those. The second is a little bit more interesting. They think they've spotted a situation where people are passing money, dodgy money, around their house in the hope of cleaning it. I'll explain a little bit more detail what that means in a minute. So they've got that big book of data. We've got a modern Oracle database to help us out here. So we've got that information stored in a nice table, transactions table, and that's got the regular transaction details you might expect, when it was made, the amount, so on and so forth, and the sender and receiver accounts. As well as the account IDs, we've also augmented this with various information about the sender, their name, their house, gender, occupation, and so on. So this will help the machine learning algorithm a lot, but it will also come in potentially very handy for our rules, so we can apply them much more easily. So we've got that for the sender, got that for the receiver, and we've got a big table of transactions, like 100 odd thousand transactions, a little bit more than that. And we've got lots of things like this. So now we want to apply the rules to this. So first thing we're going to do is pull out all the transactions with a value of exactly 10 million. Really tricky this, isn't it, Abby?
I think I might have this one, Chris. I've got this one.
Yeah.
Bit of basic SQL.
Yeah, we just need a where clause, right? Find all the transactions with a value of exactly 10 million. So that's pretty straightforward. The second one, as I said, is a bit more complicated, and I'll just spend a moment explaining what the problem here actually is. So the idea here is I've got some dodgy money from somewhere, and my hope is that I'll pay it into the bank, transfer it over to Abby, and then she'll cash it out later on. And the hope is that somewhere in this process, the bank won't realize what's going on, and we'll get away with it, right? So very simple in this instance. We're just looking from one person to another, cash it out, basically. But of course, these days, criminals are much more sophisticated, or at least so I'm told they're much more sophisticated, right? They more likely to do something a bit like this, where have a nice big long chain of transactions where I've got my dodgy money. Instead of sending it straight to Abby, I'll kind of co-opt all of you watching into our scheme and say, I'll pass on my 10 million to the next person, who will pass it on to the next person, so all 20 or 30, 40 of us here. And eventually they'll work its way round to Abby. The idea here is if we just make this chain long enough, right, hopefully the bank won't spot what's going on. I'm not sure about that assertion. The bank's probably going to spot a large sum of money working its way through the banking system, or someone will at least. But also, we can sort of spot this as well using some SQL. Now, there is a more sophisticated attack even than this. If we've got a large sum of money moving around, as I said, bank's probably going to spot this, but also any of you watching might kind of go, well, actually, I'm just going to run away with the money myself, not wait for it to get to Abby. Yeah, I'm not happy about that. I'm not happy about it. But you're like, well, you'll just take all the money for yourself and run. So there's always that risk. So rather than spread the whole money between pass it around everyone, what we can do is just divide it up. We'll say each of you get an equal share, and then I'll send that to you, and hopefully you send that on to Abby. As a criminal, a lot more attractive properties to this. Less likely that any of you are going to, or if any of you do bail on our agreement, then you've only run away with a smaller fraction. It's much harder for banks to spot this because there's smaller value transactions generally, and of course there's just far more low value transactions, so it's less likely to get flagged up, and it's much harder to write queries and things like this to spot this. There are ways, but that's way beyond the scope of what we got time for today. So for today, we are going to stick with a nice simple case. I've got some dodgy money. I'm going to send it to Abby, or one person is sending it directly to another, and they cash it out. So we're looking for transactions of the same value within a house. So imagine we're all in House Oracle. We want to look for all transfers between people of this house. We've got House Microsoft. We want to look for all the transfers between House Microsoft. So we'll see how we can do that. So the first thing we want to do is just filter down our transaction types. So we're only interested in transfers in, payments in, cashes in and out. We're not looking at people purchasing goods here. So we're just looking at cash in and transfers. And what we want to do for those transactions, we want to say, has there been a recent transaction of the same value within the house? So we can do that with this max function. We'll say, if this returns a transaction ID, if this is not null, then we're going to tag it as fraud. Fraud, it's fraud, right? Yeah, exactly. So the key thing is, what do we put in this over clause? So this is our windowing analytic function. So as I said, we want to carve the data set up. So we only consider transactions of within a house against each other. So by partitioning by sender and receiver house, only transactions within House Oracle are considered against each other. Only transactions within House Microsoft are considered against each other as well. Now note, this will, if there's any transactions across the houses from Oracle to Microsoft or whatever, something like that, they would get put in their own little pot as well. So we need an extra filter to make sure the sender and receiver house are in fact the same. You can assume there's a where clause somewhere not shown on this slide that does that. But the other interesting thing is we want to look for transactions of the same value. Okay, so we've put them in pots of by house. We also want to put those within those pots of exactly the same value. So if there's a 10 million transaction within the House Oracle, and there's two of those, they'll go in the same pot. If there's two transactions, the value of 1,000, they'll also go in the same pot. So that's what partitioning does. We then want to look going forward over time. So we're sorting by date. There's always a date component to transactions. One will happen now, the next will happen later, and so on. Pretty straightforward, right? Yeah. you look puzzled there, Abby.
Yeah, something's not quite right, Chris.
There's a problem here. So if this is all we do, there is a default windowing clause for all or for analytic functions, and that is range between unbounded preceding and current row. So this is implicit clause. Yeah, no, it doesn't sound right, does it? So what does that mean? Well, it means we are including all of the entire history of transactions plus the current row. So we'll start with the current row. That is a pretty obvious problem. We're saying if this maximum transaction ID was not null. But of course, if we include the current row, well, it's always going to be not null because we're always going to return our own transaction. Okay, bit of a problem there. We want to exclude the current transaction. But also, if we look back over the past, if you've got 10, 20, 30, whatever years worth of history here, probability, just by chance, of having two or more transactions of exactly the same value within a house just becomes very, very high, right? For pretty much all values. So we want to bound how far back we look as well. So we need to exclude the current row and put a limit to how far back we can do. And we can do that by putting some numbers in here. So range between 90 preceding and 1 preceding. So what that does is to subtract this value, that number of days, from the transaction date for the current row. So 90 days preceding and the previous day. Bit better, but yeah, exactly. We are excluding the current anything that happened today. So we're going from this time yesterday. If we've been really quick, so I got some dodgy money this morning, paid it in, transferred it out to Abby, and she cashed it out in the afternoon. We've done that all within a day, and that's not going to then get flagged up by this query, or at least not till some point later on down the line. So we want to be a bit more granular here and pick things up a bit quicker than that. So rather than 1 day, we can divide that through the number of minutes in a day. So with 1,440 minutes a day, divide through by that. So that any transactions from the previous minute or up to 90 days previous to that. So we've got our rolling window there and look for transactions of the same value. So that will show us if there has been at least one other transaction of the same value. I said if we had that big long chain where we were passing the same value around all of you watching here, there's a way we could sort of spot that at least. We can put that in with a count. If we see a lot of transactions of the same value, particularly if it's a high value, again, bit of a tip off there's something dodgy going on, right, Abby? So
Massively, yep.
Massively, right? So we can look into that and figure out what's going on. So we've got our rules now, we've got our SQL queries. I'm feeling pretty good about this. Yeah.
I've got to say, Chris, I'm quite impressed at this, range between. So, big question: how successful were you at flagging fraudulent transactions?
Okay, so this is time. This is the moment of truth, isn't it? It's a moment of truth. So, we went through, looked back at what the Hand of the King had done their analysis on, and compared our rules against that, and we found we had an error rate of about 1%. So about 1% of the time we got things wrong, and just so happens that within these data set, the fraud rate was also about 1%, right? So this is sounding pretty good, right? We've done it. We must have figured out who they are. Yeah.
Yeah. Okay. That's pretty good, Chris. I've got to say, I'm impressed at this point. So,
Yeah.
so who was it?
Shall we find out? Let's find out. Let's see. All right. So let's look. Ah, there we go. Wow, Night's Watch, right? Yeah.
They're up on that wall in the north. Nobody's keeping an eye on them.
Exactly. They've clearly been up to something dodgy. All right then. So maybe they've been dealing with the wildlings or something like that. Let's bring him in. Bring him in. Lock him up. And
lock him up. Lock up Jon Snow. He's definitely being naughty.
Okay. Cool.
But this is really good, Chris.
Yeah.
But I've got a problem.
You've got a problem.
We're still losing money.
You what?
I said we're still losing money, and just to add to the problems, the Baratheons are really, really unhappy because these rules that you've put in place are stopping their transactions from getting through.
Okay.
So why are we still losing money, Chris?
That's a good question, Abby. I think we need to think about this a bit more in detail, right? Okay. All right then. So before we dig into what's actually gone on here with our analysis, let's take a step aside and look at some theory and look at a different example. So this is an example we picked out a very long time ago. I think it was a year and a half ago now or something. It feels like forever ago. So just to be clear, before we start this, we hope you are all safe and well and happy, and there's nothing wrong with you. But let's just imagine that you are suffering, you're feeling really ill, and you've got you know, you're worried there's some rare disease affecting you. So you go to the doctor, and they run a whole suite of tests, and it turns out you come back positive for a really rare disease. So I don't know, legs falling off itis or something like that. Something unusual that very few people get. You know, something that maybe affects maybe 1 in 10,000 people. So it's an unusual disease, and the test is very accurate. So 99%-ish accurate, which is, you know, about as good as you get with medical tests. You know, people lose samples, get spoiled, and so on. So very accurate test. But it's an unusual disease. How are you feeling at this point, right? You just come. Yeah.
I'm not feeling too great. Leg falling off itis does not sound good, Chris, and this test sounds very accurate.
Yeah, exactly. It sounds pretty worrying, isn't it? You know, we've got very accurate tests that told us we've got some unusual disease which has got lots of complications to it and so on. And I think most of us, if we're in this situation for real, would be at this point kind of very rightly probably going like that, what's going on? But actually, let's dig into some numbers a little bit and see how worried maybe we should be. So let's imagine we've got 1 million people. So we've got our 1 million people, 1 in 10,000 of those roughly are going to have this disease. So 100 people. So let's look at the test results that people are going to get. So we've got 100 people who are sick and 999, whatever it is, people who are healthy. Of those 100 people who are sick, 99%, so 99, are going to get the correct result. They're going to be told they are sick when they are. One really, really unlucky person is going to get the wrong result here. They are going to be told that they are in fact healthy when they've got some rare disease. Yeah, it's not a good day, is it, Abby? You know,
no, that's not good fun. But yeah.
No, you don't want to be this person, but actually the chances of you being this unfortunate person are really, really low. They're 1 in 1 million. But things are a bit more interesting if we look at these healthy people over here. So we've got some number of 9s of these people in this group. The vast majority of them, 99%, so 989,000 odd, get the correct result and are told that they are healthy when they are healthy. But 1% of these people, these 999 whatever, get the incorrect result and are told they are sick when they're in fact perfectly healthy. That's nearly 10,000 people, right, getting the wrong result. So of the people who are told they are sick, you're actually about 100 times more likely to be in the group who are perfectly healthy and have absolutely nothing wrong with them than the people who are genuinely sick. And this example is made up, but actually it's a genuine real world problem when it comes to doing things like medical analysis, but also fraud detection. So, yes.
So in my world, we'd call this a confusion matrix, and we use it to look at machine learning models to assess how well they've done. So instead of just looking at the accuracy, we'd look at the confusion matrix to kind of understand false positives and false negatives. So when you get it right, it's a true positive or a true negative, and then you get a false positive and a false negative. So in terms of your rules, Chris, where it's not picking up the fraud at the minute, that's a false negative. So if you're the hand of the king, you want a really low false negative to stop the transactions going through. Mm-hmm. However, on the other side, the false positives explains why the Barathians are a little bit upset with you right now. Because your rules have come in, none of their transactions are going through. So they're in the false positive. They're not actually committing fraud, but you think they're committing fraud. So we've stopped their transactions and they're a little bit upset with us.
Yeah, okay. So it's we need to do this, right? We need to map the rules to this. So let's have a look and see. Actually, before we do that, let's just think about this a little bit more. So I said there was an error rate of 1% and a fraud rate of 1%. There's actually a trivially easy way to get these two figures to be match exactly. We'll see if anyone's awake and paying attention. I think most people watching actually it's a nice time of the day as opposed to us where it's the evening.
I think it's about 2 o'clock in the afternoon in
Exactly. There's trivial easy way, and have a think if you can think about how that might happen. We can get these numbers to match exactly very, very easily just by marking everything as not fraud, right? We can just say everything is not a do nothing algorithm. And maybe there's some businesses out there who do this. Certainly, in maybe not in the financial world, but in retail world and things like that. I'm sure there's quite a few who don't really just push things through and don't assess whether it's dodgy or not. So, but that's a do nothing algorithm. Hopefully, our rules are done quite a bit better than that, right? Rather than just mark everything not fraud. So, as I said,
Let's have a look.
Yeah, let's have a look. So, that's a little over 100,000 transactions. So, we're expecting about 1,000 true positives. So, things in that top left box. We want to see about 1,000 entries in there. Oh dear.
Oh dear.
Oh dear, oh dear. 80.
That's not good.
No, that's not good at all. That's nowhere near good. And actually, if we look at the false negatives, so genuine fraudulent transactions that were just let through no hassle because the rules didn't pick them up, there's like 1,200 of those, over 1,000. And we got 800 odd people being flagged up who were perfectly innocent. So this isn't good. So no. So the criminals are about 15 times more likely to get away with it than be caught, according to these rules, and you're about 10 times more likely to get picked up, completely for no reason, than actually be doing something you shouldn't be doing. So, first glance, if we just look at those overall percentages, it seemed pretty good. But looking at this, I've done bad. It's abysmal, really, isn't it, Abby? There's no
it's not that great, unfortunately, Chris. When we've dived into those numbers, that's not great.
Okay, then. So come on, then. Help me out here. Help me out. How can we do better here? How can we do any better?
Okay, so let's go into the world of machine learning, and let's explore how we can achieve maybe better results using machine learning. So in Chris's world, we have labels and no labels. So in this world, the hand of the king has been through and he has put fraud or not fraud. So he has labeled it. So that's really good. We can do supervised learning models. So today we're going to stay in the world of supervised learning. So in the world of supervised learning, in the actual tables of the transactions, Chris was using everything to the left of the table. So he was using the date and the type and the sender, and he was looking for the rules and putting them into the SQL. In my world, essentially, I'm really concentrating on the column on the right-hand side where the ones and zeros are. So I tell the machine learning model, that's the one to focus on. And the actual model, the machine, will go and look at everything else to find the patterns for me. I don't tell it the patterns, it finds them for me. It's quite nice. So we can feed this into some machine learning. Now, as a data scientist, to test our machine learning models, we often do training data and test data. And Chris, don't worry, the database has got your back and is going to help you with your SQL. So we can do something called sample 80, and it will sample 80% of the data. And because we're scientists, Chris, we like to be reproducible. So we have C124. So that makes it reproducible in the future.
Right.
To make the test data, we have a little function called minus, so we can take the other 20% to test the model later on. All good so far?
Yeah, sounds good. Sounds good. All right.
Okay, so let's get to some supervised learning models. So there's actually only a few steps to do it. The first step is to set up the model settings table. So we're going to create a model settings table, and we have two columns, the settings name and the settings value. So we're going to say algo name is naive Bayes. So it's a classification model called naive Bayes, and actually the database can do a lot of preparation for us. So we can have this prep auto and put it as on. So when there's missing values, it'll handle it for us. If it's numbers, then it'll put the median in or the mean. You can, in the auto prep, it'll also sort out any text variables, any nulls in text and char. So it'll deal with all that for us. And as a data scientist, that can actually take a lot of time. So it's really cool that the database does this for me. That's step one. Step two then is we need to build a machine learning model. Now, Chris, the database has got a function for you to do it. So DBMS data mining dot create model. So we have a few variables to put into this function. So we need to give it a model name. So game of fraud model. We're going to say it's a classification because it's a 1 or a 0. And then we're going to give it the training table. So game GOT transactions train. The unique column name is transaction ID. Well, the target column, so where the 1s and 0s is called fraud. And we're going to say use the model settings table we just created. Easy. Press go and done.
Excellent. That sounds good. All right. Is that it, right?
Yeah, we've got a couple of extra little steps.
Okay.
So
All right,
once
okay.
we've got the model, we need to apply it to the data to see how well it's done. And so again, it's just a function. It's just data mining dot apply.
Cool.
So in this one, we now tell it to use the model we've just created. So the little model that we created. We give it the test data that we created using our minus function. We say again that the unique ID column is transaction ID, and we've asked it to put all of the results into something called fraud results. Dead easy.
Okay, so now we're done. Yeah?
Now we're done. Now we're done. So now we've got our results essentially. So let's find out how well we did.
I'm excited. I'm hoping this is going to be really good, right? Okay, let's see. Moment of truth and hang on. Error rate of 3%. You've done worse than the rules here, Abby, right? Or looks worse than the rules,
okay,
right?
On the surface, it looks worse than the SQL rules. But, Chris, we did have to dive into your numbers to find out what was going on. So I think it's only fair we do the same with the machine learning.
All right, I'll let you off. All right, then.
So because I'm a data scientist, I have another little function that I can use to do my compute confusion matrix. So I don't have to use SQL, I can ask the database to do it for me.
Sure.
So in this one, we send it the results table, we send it the test data, we tell it the transaction ID is our unique one and that target column's fraud, and we ask it to compute our confusion matrix. So once we've done all that, we can output a result.
Okay, let's look at it. Let's say okay.
Okay, I think I'm doing a little bit better in the true positives there.
Yeah, you're catching about 10 times more people than I am. Okay, so I think the bank are going to be a bit more happy with you, right?
Yep, and that 451 is much lower, so less people are getting away with fraud than yourself. But you're still twice as likely to get away with fraud than I am to catch you.
Yeah. But okay, hang on. But remember those Baratheons? You know, we've got what 4,500 false positives. So actually, you are what about 3 times? Well, actually, probably closer to 4 times more likely to be flagged up than actually be, doing anything dodgy.
So that's true. I am going to stop the transactions going through, and yes, I am probably going to really, really, really upset the Baratheons.
Okay. All right. But still, we are catching a lot more people, right? So I think we need to find out who's actually been doing this, don't we?
Sounds like a plan. So fancy using a bit of that fancy SQL again.
Okay, let's do some SQL. All right. So once you've applied the model, we get a nice big table like this, 1s and 0s and so on, don't we? So what we need to do is for each transaction ID, so 1 is fraud, 0 is not fraud, pick which of these rows has the highest probability. So which of these is closest to 1 in the probability column for each transaction ID. So there's various ways you can try to do this. I'm going to use the row number approach. So split up by transaction ID, so partition by it. So we only compare the 2 rows for each transaction ID against each other, and then sort by that probability descending, so we can get the one that is closest to 1. I'm saying 1 a lot there in that sentence. But, so whichever of those rows has the value 1, we can then pull it out in a outer query. So this is in a subquery. So that will pull out all those. We can then apply that join that back to our original data set to see who all the baddies are, and let's see who's doing the worst here. What do we think? Oh, it's the Lannisters. Of course, it's the Lannisters. Yeah.
Sat on the Iron Throne.
Yeah, exactly. 10 times as many dodgy transactions as everyone else. Clearly, I think we need to get them in for questioning, right?
Yeah,
You know,
get them in.
get them in. Alrighty then. Okay, so we're doing pretty well here, but I think we could do better, right?
Yeah, I think we can do so much better. So, Chris, I think if we combine your SQL with my machine learning, I wonder if we're going to do better.
I think it's worth a try. Let's see.
Yeah, so in the world of data science, one of the approaches you can use is something called the CRISP-DM, so the Cross-Industry Standard Purpose for Data Mining. And it's very iterative, so you try a model, you learn from it, you try another model, you learn from it, etc. And in this case, we're going to put together your SQL rules and my machine learning, and hopefully we're going to save the 7 kingdoms for the hand of the king.
Excellent.
Sound like a plan?
Yeah, that sounds like a plan. And so we really want to catch people right here, don't we? Whoever's been conning them out of the Iron Bank, we want to find them. So regardless whether machine learning tags it or SQL tags it as fraudulent, we want to pick that out. So essentially, we'll just join the two data sets together and find which one of those has a fraudulent flag. If either of those has a fraudulent flag, we will say it's fraudulent. And if we look at our confusion matrix now, it looks kind of similar to the one after Abby, but it's slightly better. We're actually catching nearly 900 people, so we're doing better than we've ever done. You're less likely to get away with it than ever, so it's under 400 people getting away with it. But the flip side of this is we are now, annoying a lot more people with either blocking their transactions or those automated phone calls saying we think we've spotted some dodgy call stuff on your account. So it's a balancing act, isn't it? If we compare how these all stack up, SQL is the best in terms of just not annoying your customers, but combining them actually gives probably the best business impact, isn't it? And this is a conversation. It's a business conversation to have, really, isn't it, Abby?
It is, yeah. So I've seen this in some of the institutions I've worked with, where at the boardroom level there is a balancing act between stopping fraudulent transactions going through, which is what we're seeing with the SQL and ML, and therefore protecting the risk side of the bank. But it does upset customers and can change the customer experience, which is what you're seeing on the right-hand side, and that therefore the Baratheons would be very upset that their transactions aren't going through. So there is a balancing act, and it really does depend on what your business question is. Is it to reduce fraud, or is it to find a happy medium between upsetting customers and fraud?
Happy medium. Okay, so well, let's just kind of recap what we talked about a little bit, but let's think about it in a different way. So we talked about SQL rules versus machine learning. There's another general way we can think about this, and that is deterministic versus probabilistic. And so the SQL rules is like the deterministic approach. You've got a big long list of things and says, if this criteria hits, then it's fraudulent. If this criteria hits, it's not fraudulent, and so on and so forth. And I say deterministic because if you pass in some inputs, run it through the program, you will know exactly what output you are going to get. And this makes a lot of advantages for us as developers. We know exactly how the program is going to behave. So, we've talked about SQL rules, but the fact is you give any competent programmer a big list of rules, they'll find a way to do it, whatever programming language they're happy with. So key thing is when we pass some values in, we know exactly what we're going to get out at the end. Whereas it's a little bit different in the machine learning world, isn't it, Abby?
It is. So in my world, we get a probability, but it's how close to 100 do you need to be to feel confident or certain that it is that value? Or how close to 0 does it have to be that you're really confident it isn't that? And is there actually a very grey area where you're almost sure or you're almost not sure? So is 70% good enough? 80% good enough? Or does it have to be 99.9% for it to be good enough? So mine's more of a scale, and it depends where the business want to draw the line on the scale for me to say whether it is or it isn't.
Yeah, it's a tricky decision. Everyone's got different risk tolerance as well. In terms of different people will be happy with 70% than 90%. Just generally. So, okay, let's review. As I said, so with SQL rules, we've got this deterministic approach, and as I said, the nice thing about this, you put some inputs in, and you know exactly the result you're going to get. And particularly for things which are very high risk, and you want to be absolutely certain that you flag them up, it's maybe worth just building in some rules for those. So, personal example, last year, I think it might have been a little bit over a year ago now, I got a new laptop. Shortly after getting that laptop, I logged into my bank, my online banking system, and made a new large payment, a new large one-off transaction. Obviously, some alarm went off in my bank because this is the first time I had logged into my account from my new laptop. And so they kind of like, a few hours might have been the next day, I got one of those calls like, was this really you? Did you really authorize this transaction? It's like, well, what are they worried about? Maybe because it's a new device, someone has stolen my credentials. They got my username and password, got into my account, and are trying to clean me out. And they want to protect against that. And it's a high risk thing. Um, it's unusual as well. It's not very often we get new devices, once a year at most. A lot of us less frequently than that. And new payments again, if you do them more than once a year, you'd be unusual. So two of them together, you probably want to check those out because they don't happen very often. So we can be sure if we've got these very, very high risk scenarios that they always get flagged up with the rules-based approach. Whereas you can't quite say that, can you, Abby?
No, because the machine finds the patterns, then it'll weight them and you get a probability scale. So some will come out at 70%, some will come out at 90%. And there isn't really a guarantee that given the same data every single time, you'll get exactly the same because the data's slightly different. Male 35 and male 36 might just weight slightly different and the probability value coming out might be slightly different. So again, it goes back to the question of where's the business risk tolerance? How high a percentage do you need? But I can't guarantee you that outcome.
No. So yeah, but the big advantage you do have is that the machine figures out these rules, right? And if you're trying to build a rule-based system, it's very, very difficult to do that correctly without a lot of domain experience. If you get a bunch of people, sit them in a room who don't really know the system or the types of transactions you're dealing with, they'll come up with some rules which may not apply. They'll miss some obvious cases of fraud, and they'll pick some things which are just normal. Another personal example. So 15, 20 years ago, in the relatively early days of online shopping, buying things on the internet, I had a credit card. And they had some simple rules-based system, I'm sure, where if I spent more than about £50 online, I'd get one of those automated alerts. Was this really you? Did you really make this transaction? And they were quite worried about maybe someone stolen my card number and was using it to buy things. Sounds like a sensible rule, right? Problem is, I trip this rule really often, on average probably about once a month. It happened, I got this alert so often, I just switched off. I stopped paying attention. First time you're like, aha, second time you're okay, I know, and 10th, 20th, 30th time you're just like, okay, whatever. Maybe someone could have stolen my card and I just wouldn't have not paid attention because at that point you're just not listening anymore. It's the boy who cried wolf problem. So you need that domain knowledge to catch the obvious stuff and not flag up stuff which is just perfectly normal and just day-to-day transactions as well. You need that domain knowledge, whereas you've got a bit of a leg up there, don't you, Abby?
Yeah, because the machine's looking for the rules, we can actually find patterns that humans might miss, as you've kind of said, Chris. So if we think of something like cryptocurrency, when that came out, the banks didn't have rules. There were no rules as to what was or wasn't normal in there. If we look at the more recent pandemic, when people have gone into lockdown, again, people's behavior has changed, the patterns have changed. So machine learning will be able to pick that up rather than humans. So you can miss the obvious fraud from your rules, but with machine learning, it picks out some of those more obvious ones and flags them straight away for you. So there's some advantages. The other big advantage is if you think of a human trying to look at hundreds of columns, that's when you're going to miss a rule. Whereas a machine, it doesn't matter how many columns you throw at it, it'll just crunch through the data.
Yeah, that's a good point. I was talking about the hand of the king pouring through pages. We're not going to turn pages of a book anymore, but still, anyone who's ever spent a time looking in a spreadsheet trying to find values will know you're going to miss stuff. Once you get past a few hundred rows, even a few hundred, you're going to miss stuff. Our brains just cannot cope with that level of complexity, can it? But going back to one of the advantages of SQL rules is that for the most part, this uses existing skills. As I said, you give any competent programmer a big list of rules and say, go make this work, they'll find a way to do it. And they can write unit tests and whatever and make sure it behaves exactly as you want to. So for many of you watching, writing a SQL rules-based system allow you, or even whatever rules-based system, will be something you're kind of familiar with. But it's also about the business skills, something we kind of hinted on a bit when we're talking about the probabilities. Like say, people in the wider business understand the concept. Okay, if there's a large transaction from a new device, then we're definitely going to flag it up. A lot of people don't really get there's a large transaction from a new device, so there's a 70% chance we're going to flag it up, do they? So it's just like, it's not just the existing technical your development skills, it's also the wider business understanding what the heck it means when we get certain results, doesn't it?
That's where probably mine's slightly different. We're still inside the database, which is great, and we can still tap the PL SQL side of your skill set, Chris. But you're right, when we then go and try and present it to the business, there's a bit more of a data story to take them on, to let them understand what tolerances and understand setting 70% or 80% as being the probability, or even just accepting the maximum. What if it was 51 and 49? Is that a good enough split for you to accept that 51% means it is fraud? So these are the kind of stories and kind of approaches you need to take through the business through so that they understand what they're signing up for when they do machine learning.
Yeah. So, but on the whole, I must say, I do like this. I think there are definitely a lot of advantages and a lot of ways that machine learning can sit alongside existing rules, augment it, and improve the quality of decisions that you're making. But there's still something that's kind of bothering me a bit here, Abby, right? I've got 4 letters that I want to mention to you, and that is GDPR, right? With my rule system, I know exactly, when my Baratheons are going, why the heck are you doing this? What's going on? Well, we can go, oh, okay, you've hit this rule, we can tweak that or make some adjustment. We know exactly why that has happened, right? You can't say that, can you, Abby?
No, in the world of machine learning, this is a kind of problem that we have, and some people call them black box algorithms because you can't see what's happening inside them. You can't pull them apart and say exactly why you've been flagged for fraud. And if you have to be able to explain that to them, that's really, really difficult and can't be done. So it's something called explainable AI is that area that we're researching at the minute to try and explain what happens inside the black box. There are some algorithms that are less black box and slightly easier to understand, but again, they take time to walk people through rather than a simple if this, then this, if this, then this. So yeah, Chris, on that one, I'm afraid the rule base wins.
I think, many of you watching might be thinking GDPR, that's about European citizens, that doesn't apply to us. This rule applies to any system that catches data on European citizens, even if you're hosting it in Paraguay or wherever you live. If you've got customers who are European citizens, which sadly will exclude us in about 3-4 months' time, Abby. So
Yep.
you can capture all the data you want on us in a few months, but the rest of Europe. So if you do any capturing, you have any European customers, this still applies to you, and it's likely there's just more and more countries applying their own versions of GDPR as well, with their own local laws. So this is something you will have to consider at some point, if not right now. So, yes. Okay then. So, where have you go with this then, Abby?
Yeah, so from our perspective, I guess we wanted to take you on the journey of false positives, false negatives, and pulling apart when you kind of go to present these figures. So sometimes accuracy scores are not quite as accurate as they seem, and you need to drill down, and something like a confusion matrix helps you understand what's really happening when you're doing this kind of work. And really the question is, which one is your company ready for? Are you still in the rule-based world and you need to kind of look through each rule and write them down and be able to explain them to customers? Or actually, have you started down the journey of machine learning? And really, could you use them in combination rather than independently? So I think that's it from us, Chris.
Yeah, that's good. We'll fix the world, right?
Exactly. We're going to fix the world and solve all the fraud using SQL and machine learning.
Yeah. Alrighty then. So I think this is the end of our allotted time. I'm not sure if we're able to spend some time taking questions, but either way, it's great. Glad you can all join us.
I think you have the time to take questions.
Okay. Yeah. If you got questions, want to put them in the Q&A or the chat, and we can take those. So, just if you are got a question, one thing that has come up in the past that people said, well, if you've got these rules and they're not, you've got machine learning and it's not flagging up things that you want them to, why don't you change the algorithms and stuff? First up, as Abby was saying, with that iterative process, you will kind of keep doing that. But of course, there might be some things you just know they're high risk. You just know you always want to flag them up. Instead of kind of chasing the perfect algorithm or the perfect model that will flag them up, it's very easy to just have some simple rules. If these really risky criteria are hit, do it. Otherwise, let machine learning find more harder to find stuff, or the less high risk or less high clarity things. So.
I know also in the past we've had the question of where is machine learning algorithms in the database, or what versions. So as of December 2019, Oracle made the machine learning in the database freely available. So thank you, Oracle, very kind of you. So it is available across the databases, so the functions that we've talked about here are available in your database, and you can have a go at them. They're obviously in the autonomous data warehouse as well, which is tuned for these. And yeah, there's a machine learning notebook in the Zeppelin notebook, so you can try them there. But yeah, that's usually a question we get quite a lot. Can you do it in any Oracle database? And thank you, Chris. Yes, Oracle has now made it available.
Yeah. Okay.
Okay.
Okay then.
I think this is it. I don't know if you have something else to add. If you don't, I would like to thank you very much for joining us today. También quiero agradecer a todas las personas que han estado hoy aquí con nosotros participando de la conferencia de Chris Saxon y su compañera Debbie, que nos han hablado sobre el juego de la detección de fraudes con SQL y Machine Learning. Un tema súper interesante realmente. Les recuerdo que todavía tenemos charlas hasta el viernes, así que manténganse atentos y manténganse conectados. So, if you are able to assist, we already have some conference until Friday, so please feel free to join us. Thank you very much for being with us and for sharing all this knowledge that is really interesting with us.
Cool.
Thank you.
Right then.
Thank you. Goodbye.
All right, cheerio then.
O si hay que regresar manualmente, hay que meter un... Sí.